Hey everybody, welcome back. Hope you're having a good time at Pivot today. This has been a fun day full of a lot of substance. So we're segueing into another new test that we're doing where we're going to do a very short technical presentations to give some context to a panel that will happen after the presentations. And what this is essentially, the panel is gonna talk about the use of data and standardization techniques in the oil and gas industry and how we might transition those techniques into mitigating induced seismicity in the geothermal context. And so the next three technical presentations are going to involve oil and gas brains that have been thinking about data and using data in the oil and gas context, but have been invited to start engaging in geothermal by entities that have started working in geothermal over the past year. And so this will give some food for thought as we go into the panel session. So without further ado, I'll get out of the way and introduce our first technical presentation. This is Sashi Gunturu with Petrabytes. Take it away, Sashi.
Yeah, thank you, Jamie. So I'm Sashi Gunturu with Petrabytes. So today I'll be talking about understanding the induced seismicity effects, mainly how we are utilizing all the subsurface data and then further doing geomechanical modeling. So if you look at induced seismicity, so it's basically a pre-existing understanding how the pre-existing faults are slipping, and that can be assessed using the geomechanical model. So we do the slip tendency analysis, and primarily we are analyzing all the geomechanical stresses and understanding the pore pressure. And once we have this understanding, then we'll be able to understand if the plane is stable or not. So let's briefly look at some of the geomechanical modeling concepts. So if you look at all the subsurface data, you have a variety of data sets here. Like, for example, you have all the well data, you have all the horizons, you have all the thin sections. So what's above at a very high level, the entire field data, and also what's at the well level. So you have all the thin sections, the discrete fracture networks, also the geobodies, the horizons, reservoir grids. And then you also have a lot of seismic and microseismic measurements. And then you have the completions data, and then you have the GIS and cross-section data sets, and also the entire geology. Off late, there has been a lot of measurements using the fiber optic data. So you have acoustic sensing and temperature sensing, and also strain sensing. So these are like very large scale data sets that are time series dependent. So if you look at oil and gas subsurface data, primarily you have, it's basically a lot of variety, lot of 2D and 3D and also time series data sets. And all of them, in order to get a contextual analysis, you need to have a common georeferencing. So with all the advent of cloud computing and distributed computing, so you can have all these different data sets that are coming at different frequencies from different sources. And you have all these different data pipelines. So the first step is to aggregate all of these different data sets. And because of the scale of the data sets, you need like high performance computing with in-memory clusters and all of that. So the cloud providers, especially the three major providers, and also the distributed computing is playing a major role in synthesizing all this data and preparing the data in a seamless data exchange. Off late, all the oil industries, all the different companies, the vendors, the cloud providers, they've all together formed what is called the open subsurface data universe. So the primary goal is to have a common seamless data interoperability between applications and vendors. So if you like big companies like Chevron and Exxon, they have lots of data sets, lots of vendors to manage. In order to have a more comprehensive, the goal is to have a standardized data exchange between systems. So that means you have all this structured, unstructured data, and also the real-time data. So you're essentially forming what is called an energy delta lake, where you have all the different kinds of data sets, all the upstream data, pipeline data, all these different kinds of data sets. So this will enforce a kind of a clean data governance. And then the OSDU is defining a set of APIs so that the systems and vendors, they can exchange data with a common reference. This is similar to what the healthcare is doing with the HL7 standards, right? So the energy industry is trying to standardize all the data exchange between applications so that you get a much better subsurface analytics. And then you're going through all the cleansing workflows, essentially going through all the governance and applying different rules. For example, if you're looking at a geologist, avoiding any duplicate formats, processing the data in a proper synthesized way, especially the time series data sets, all of that have to be contextually analyzed in order to have a clean data set for all the microseismicity. So in this case, now moving on to, so once you have all this data analysis, data preparation, the next step is to understand all the different stresses. So typically when you're looking at a geomechanical model, you're looking at the vertical stress, the minimum and maximum horizontal stress, and also the formation pressure. And then, once you understand all of these, that is when you go deeper into, you need to model the stresses properly. So the first step is to understand all the overburden pressure, the vertical stress, and by looking at compactions, the buoyancy, the capillary pressures, the fluid pressures, and the fracture gradient, and also the minimum and maximum horizontal stress. Then we look at all the drilling events that are happening. So this has all the mud logging events. So pretty much all the different events that are happening, like loss circulation, ballooning effects, all of that need to be populated into analyzed for the drilling events. Then we need to characterize the lithology. So by looking at the gamma response, like the well logs, gamma response, you can now characterize the lithology. Again, here you're looking at the formation tops, the well casings, and also the lithology that is based on the gamma cutoffs. And then you're characterizing this lithology. And then once you have that, then you're applying various correlations and you're calculating all the different rock properties. So this is at the well level. Let us say you have hundreds of wells, then you need to do for all of these different data sets, different wells. Once you have the rock properties, then you can go to the vertical stresses. And then you're analyzing the formation pressure. Here you're looking at the buoyancy effects and all of that. So that is how essentially you're looking at all the different logs, the compaction effects, and then calculating the formation pressures. And then you apply the Moore-Coulomb criteria to visualize all the different stresses. This is at the 1D level. Now, if you're moving into the 3D level, because it's a much complicated problem. So typically, when you're modeling the reservoirs or the geomechanical models, you are looking at what's above the reservoir, which is the overburden, and then what's below the reservoir, which is the underburden, and what's on the side of the reservoirs, which is the side burden. So you're looking at, in this case, what you're visualizing is the reservoir grade. You have all the faults, you have all the DFNs, the discrete fractal networks, and also all the horizons. So once you have it, you're looking at, here you have a visual of the contextual data analysis, where you have all the different wells, you have all the horizons and the DFNs, and also the reservoir grid. So ultimately what you're doing is coming up with a 3D stress model, where you're looking at all the different stresses and also 3D properties. So you're populating, in this case, you have actually defined all the reservoirs with all the grids and everything, and what's above all the 5 zones, which is the overburden, underburden, and also the side burden. And then you're creating a geomechanical stress model for the entire field. So you have all the wells, and now you can model the stresses. So then comes once you are using this the completion design, you're now here, you're looking at the fracture geometry. So applying the geomechanical concepts, you are basically qualifying what is the fracture efficiency. Like, do you need 3 stages or do you need 2 stages? And then in this case, you're also characterizing how the fractures are propagating when you're pumping the proppant. In this case, you're looking at how the fractures are propagating, how they're opening and closing. So in this case, so ultimately the goal is to understand how what is the fracture efficiency of your hydraulic fracturing job, and then how many stages do I need? Okay. So off late, that is on the modeling side. Then you have the new advances where you are looking at real-time monitoring of these events using distributed acoustic sensing. So typically the acoustic sensing applies for conventional well modeling, pipeline monitoring, and hydraulic fracturing, and also carbon storage monitoring. So in this case, a fiber is like a continuous sensor where you're getting measurements every 1 meter in this case. So, and there are different kinds of sensor measurements. You have acoustic sensing, you have temperature sensing, you have strain sensing. And these are coming at a very high resolution and pretty much in real time. So for example, if you have several offshore wells, you have permanent installations of this, and you're continuously gathering data. For example, we have been working with one of the operators where they've collected more than 160 gigabytes of temperature profiles on these wells, high dollar wells, over a period of time, over 1 year. So essentially, it is generating a whole set of large data sets, typically in gigabyte and terabyte scale. And the idea is, by looking at very high resolution spatial data, you're now able to characterize how the fractures are propagating, or in this case, how the wellbore events, depending on the application. So if you have pipelines, you're looking for leaks. If you're looking for hydraulic fracturing, you're monitoring how the fractures are propagating. So here is an example of how you're monitoring the events using the DAS data. Again, this is the DAS signature. You're analyzing the data. Now, typically, as I mentioned, the data sets are really huge. So what you do when you have this, so the DAS is basically providing an acoustic signal, which is an amplitude. And then using machine learning, what we do is we remove the noise in this case. And then ultimately what we are calculating is the frequency band and also the spectral energy. So once you have all these data sets, you're now extracting the most meaningful feature based on this acoustic sensing. So for example, if there is a rock movement versus a fluid movement, based on the frequency and also applying machine learning techniques, we'll be able to identify the signature or the spectral energy that is coming from the distributed acoustic sensing. So ultimately, what you're doing is we are creating a representative log, like based on the original image, and doing all the classification and coming up with a representative log, the acoustic signal, which can be correlated again, contextually analyzed along with other well events or any kind of field events. So the idea is these data sets, because they're significantly huge, you need to apply machine learning in order to extract only the meaningful, the rich data out of these acoustic signals. So in the first sequence of geomechanical modeling, we are using analytical solutions and also geomechanical simulations and looking at all the subsurface data and coming up with a model. And in the second phase, we are looking at applying distributed acoustic sensing, how you can monitor these fractures. So in summary, what I would say is, this is an example of how geomechanical modeling has been used for a variety of applications, both for conventional, also for induced seismicity. And the idea is it takes data sets from different sources, and they all are aggregated with a common georeferencing. And typically the 3D stress modeling based on this pre and the post processor, those have been aggregated. And the idea is with all this data aggregation, you can now define very complex meshes, especially how the fractures are propagating. So the mesh building of how you represent the stress field is very important. And then monitoring with sensor data involves big data processing and also machine learning to extract rich data. And in all of these, ultimately, you have to come up with a contextual analysis to understand various events. And as I mentioned, like the data integration and also physics-based modeling and simulation modeling with ML, along with cloud-based distributed computing, is making this whole process of modeling complex geology and also the stress fields with geomechanics possible. So with this, I would like to conclude and thank you, Jamie. Hope you all have a good conference. Thank you.